classic way to make an ether is with an alcohol. And remember, that's a molecule that has an OH coming off of it, and an alkyl halide. So alkyl, that just means you have some carbon chain, and on that carbon chain is going to be a halogen. The symbol for a halogen is usually X. When they explain it generally, it's everything in group 7A. So that's fluorine, chlorine, bromine, or iodine. Now, fluorine is really small, so it has a hard time existing by itself, which means it has a hard time coming off of molecules, because it's so small, you're trying to fit this full negative charge in a tiny, tiny space, and that makes it very reactive. So it tends not to want to come off of molecules, so the molecules then wouldn't react, and so we don't use that one that much. So in practical terms, when they talk about alkyl halides, they're talking about a carbon chain that has chlorine, bromine, or iodine on it. Okay, so if we combine these two things, an alcohol and an alkyl halide, we can make an ether. And the process for doing this is called the Williamson ether synthesis, after the scientist who first developed it. Okay, the alcohol we're going to use is going to be the nucleophile. Now here I will just use a simple alcohol, ethanol, and for an alkyl halide I'll just use a similar one. Let's say 3 carbons and then our halogen, say chlorine. So those are the two molecules I'll use as an example here for how to do this. Now, the alcohol is going to be the nucleophile, and you'd remember that you'd recognize nucleophiles and electrophiles in the following way. You have nucleophiles and electrophiles. Nucleophiles are either going to have a full negative charge, a partial negative charge, lone pairs, or pi bonds. And electrophiles will either have a full positive charge and a partial positive charge. And when you want to describe how a reaction happens, it's important to find these characteristics, these centers, nucleophiles and electrophiles, because the reaction is going to happen when the negative charge is attracted to the positive charge. So on this alcohol that we have, this oxygen is slightly negative because it's very electronegative, and it has the lone pairs. So there are two things telling us that that is the nucleophile. And that's going to want to attack the alkyl halide. Because if you look at the alkyl halide, chlorine is pretty electronegative. It's going to be slightly negative, but bonded to it is this carbon that's slightly positive. The electrons are going toward the chlorine, and so they leave a sort of positive charge behind the place where they're leaving. Okay, the only thing is, this oxygen is also kind of stable by itself. There's not a full charge here, and so it's not that strong of a nucleophile. It's a decent nucleophile, just not a very strong one. So to make it stronger, so that the reaction is more effective and efficient, we can take this alcohol and treat it with a base. And a really good base to use is sodium hydride. Sodium hydride. This is an ionic compound. Sodium's a metal, hydrogen is not a metal. And so really this can separate into 2 ions. Oops. The 2 ions would be sodium with a plus charge and hydrogen with a minus charge. So when you add sodium hydride to this, to your alcohol, the negative charge on this hydrogen, and this is really unstable because hydrogen is so small and you have a full negative charge on it, that hydrogen wants to steal whatever it can. And the thing that it steals is this hydrogen on the alcohol. That bond is already a little weak because the electron density has gone toward the oxygen, and the hydrogen is slightly positive. So the electrons here in this bond go onto the oxygen, and now you get this molecule so these two electrons there used to be the electrons in the bond. You get that molecule, and then these two hydrogens stick together, and that's hydrogen gas, so that would just bubble away. So we can disregard that. We're not interested in that right now. Same with the sodium. It's floating around there somewhere, but it's not our molecule of interest. So we have this here, and this is called an alk oxide. Now the alk is referring to the carbon chain, so in this case it would be, because the carbon chain has two carbons, this would be F oxide. The oxide is just telling you that the oxygen has a charge on it, negative charge. Okay, so we've taken our alcohol, we treated it with sodium hydride, which was a base because it stole a hydrogen. We treated it with sodium hydride in order to turn what was an okay nucleophile with a partial negative charge to an awesome nucleophile with a full negative charge. And now that we have that, we can introduce our halogen and our alkyl halide, and this awesome nucleophile can attack the slightly positive electrophile. Remember, these curved arrows always start at electrons because they show the movement of electrons, and they point to the electrophile. That carbon that it's pointing to, that it wants to stick to, already has 4 bonds, so if this is going to stick to it, something else has to come off, and that's going to be this bond that's already partly broken because of the separation of charge. The electrons there are going to go onto the chlorine. And so you would be left with those 2 carbon chains attached to the oxygen, and then chlorine would be on its own somewhere else. 3 of these lone pairs were already on there. This 4th one came from the bond. So notice that what we ended up with, this right down here, is an ether. Right? We've got that oxygen with 2 carbon chains on each side. So we ended up with an ether, and we made that ether by combining an alcohol with an alkyl halide. One key thing to notice is that this middle step right here is an SN2 reaction. You have the nucleophile coming in, this first here, and the leaving group leaving at the same time. 2 things happening at the same time. In order to substitute one thing with another. So you're substituting the chlorine with the oxygen. So substitution, it's happening because you have this beautiful nucleophile that's attacking, and 2 things are happening at the same time. The nucleophile is attacking and the leaving group is leaving, so it's an SN2 reaction. And that would be something that you would have studied in depth in Organic Chemistry 1. And one thing that you want to remember about that is this nucleophile attacking is one of the key steps in that. If that doesn't attack, then the reaction goes really, really slowly. It essentially doesn't happen. But in order for it to attack, there has to be room here. And so SN2 reactions will really only happen if the carbon that it's trying to attack is either methyl, so just bonded to hydrogens, primary, so that would be if it were bonded to one other carbon, or secondary, that's if it's bonded to 2 other carbons. But if the carbon were tertiary, so if it's bonded to 3 other carbons, that would be tertiary, then the SN2 reaction will not happen. So because the way you're making these ethers involves an SN2 reaction, you need to make sure that the alkyl halide is either methyl primary or secondary. So the alkyl halide must be methyl primary or secondary. And the reason why I didn't include this fourth thing is because in all of these cases, the fourth thing would be the halogen, the leaving group that would have to come off. Okay, that being said, we can approach question 14.5. And this is asking for two things. It wants to know the reagents you would use, and so we know we're dealing with an alcohol and an alkyl halide. You just have to be careful that the alkyl halide is methyl primary or secondary. And the second thing it's asking for is to draw the mechanism for the reaction. Okay, so first, with A. So with A, you notice the oxygen here, that's the ether oxygen, and so we have two possibilities. We can either take the left side and make that the alcohol, and have the right side and make that the alkyl halide, or we could have the left side be the alkyl halide and the right side be the alcohol. Now here I'm using chlorine, but it could have been bromine or iodine also. Okay, well we want because it's an SN2 reaction, we want the alkyl halide to be as little substituted as possible. We want as little hindrance there as possible. So this carbon is bonded to how many other carbons immediately? Just one. So this is primary. That's a primary alkyl halide. This carbon, the one that's attached to the chlorine, that's bonded to how many other carbons? 1, 2, immediately. And so that is a secondary alkyl halide. In other words, this one is more crowded. And because it's more crowded, the SN2 reaction won't work as well. Because when the nucleophile tries to attack, it'll just bump into those carbons, and it won't be able to. So that is not the one we're going to choose. We're going to go with this other possibility here. So here, when it says to explain your reasoning, so these are our reagents, and when I'm explaining my reasoning, I would say these would be the reagents because the alkyl halide is less substituted. Oops. The alkyl halide is less substituted. And so the SN2 reaction will be more efficient. Okay, so we'll take that little explanation, keep it up in the corner. So now the second part is to, once we have that concept down, the second part is to draw the mechanism for the reaction. Let me put this to the side. The first step is to take the alcohol, and let me just expand this a little bit. So we have that hydrogen there. Take the alcohol and combine it with sodium hydride. Remember, that's that ionic compound where hydrogen has a full negative charge. That hydrogen then, and remember that oxygen is really electronegative, it becomes slightly negative in anything it's bonded to, it steals the electrons from, those become slightly positive. The easiest thing for this hydrogen to do is to steal the other hydrogen. Hydrogen can only form one bond, So if it's making a new bond, the bond that it has to break. Those electrons go to the most attractive place that's nearby, that's the oxygen. And so you're left with, you're left with this alkoxide, and that'd be cyclohexoxide, and the hydrogen gas, H2 gas, which just bubbles away. So you wouldn't really have to list that, but it is there. Okay, so you take that, and now that you have that awesome nucleophile, the reason we did that was to make something that had a partial positive charge, a partial negative charge, this oxygen, give it a full negative charge so that it would react much more efficiently. Now that we have that, we can react it with our alkyl halide. And this alkyl halide is slightly polar. The chlorine is a little electronegative. It's just underneath fluorine, the most electronegative element. So it steals electrons for itself in the bond, becomes slightly negative. The carbon it's bonded to is slightly positive. And so now that we have these, that electrophilic center identified, that blue delta plus, we can take this negative oxygen, it attacks that carbon there. That carbon already has 4 bonds. If it's going to make this new bond to the oxygen, one of them has to break, and the weakest bond is this bond to chlorine. So chlorine comes off, and we would be left with the exact molecule that they gave us originally, that they wanted us to make. And the chlorine, the minus chlorine, is floating around. If you want, you can imagine it combining with the positive sodium from earlier. So these two. So maybe NaCl. Those aren't really the point. The point is the ether that you make. And so that would be the mechanism for drawing that ether.